Three common topologies which have disadvantages are the star network, ring network, and the backbone with star network. The reason why both the star network and backbone with star network are discouraged is because it purposely extends the length of the stub from the main transmission line. The ring network is discouraged because reflections from nearby connection points are more likely to degrade the signal integrity at the intended receiver and may also reflect back into the transmitter. If any of these topologies must be used, the data rate should be drastically reduced to ensure reliable communication. The RS-485 standard suggests that the nodes be networked in a daisy chain. In this topology, the participating drivers, receivers, and transceivers connect to a main cable trunk via short network stubs. The interface bus can be designed for full duplex or half duplex transmission. An alternative to the daisy chain topology is the junction box approach. This should be implemented in a way to minimize stub lengths and thus reduce reflections. If a non-ideal network topology must be used, it is best to insert a repeater node at each junction. The stub length in this diagram is defined as the T-junction from where three lines intersect to the device pins. For the daisy chain topology, this occurs on the PCB board where the two joining transmission cables and the traces to the RS-485 transceiver. For the junction box approach, this occurs at the main transmission wire and the joining wires into the device pins. Because the daisy chain topology allows for much smaller stub lengths to be generated, this helps to reduce the reflections into the main transmission line, which is the main reason why this topology is preferred. The junction box approach can also work well, but ideally the length of the stub should be minimized to reduce reflection. In cases where the stub length cannot be reduced to a reasonable length, the data rate may need to be slowed down in order to reliably communicate. This is a general rule of thumb, not a firm rule. The maximum acceptable stub length can be calculated using the equation provided. TR is the RS-485 driver's rise time and is found in the datasheet of the device. This is measured from 10% of VCC to 90% of VCC. V is the signal velocity, which is a function of the dielectric material of the transmission medium or cable. This information can typically be found in the datasheet of the transmission cable. This measurement is expressed in terms of percentage of a factor of the speed of light. C is the constant for the speed of light. Terminate the two furthest points of the bus with resistors equal to the characteristic impedance Z0 of the transmission cable. The termination resistance should match as closely as possible without dropping below 60 ohms, or 54 ohms if the transceiver's loading is included in the calculations. External failsafe resistors can increase noise immunity of the receiver under bus idle, short, and open conditions. An apt note on how to calculate the failsafe resistors and termination resistors is linked below the video. So how can you tell an RS-485 transceiver has a built-in failsafe? There are two ways this can be checked. The first way is to just check the front of the datasheet. This is typically a feature on the front. The second way is the electrical parameter V input threshold, plus and minus, can be checked. A transceiver with failsafe biasing typically will not center the threshold values around 0 volts. The values expected from failsafe biasing receivers should be negative values. Please note that some of the newer RS-485 transceivers include circuitry that center its V input thresholds around 0 volts and can still provide failsafe biasing. This check method, though, should still work for a majority of RS-485 receivers. Should I provide external biasing even if my transceivers all have failsafe biasing? This is not necessary because all the transceivers should still hold RX in a logic high state in the event of a short, idle, or open condition on the transmission line. If external biasing is used, the receivers may see the benefit of additional noise immunity. The downside to the external biasing, however, is increased power consumption. Because there's a path for current to flow from VCC to ground with the failsafe biasing resistor at all times. If one of my transceivers has a failsafe feature, does that mean my network is failsafe? If a transceiver features internal failsafe biasing, in a majority of cases, it applies only to that receiver. It won't carry forward to the other nodes in a network. This is different from external biasing, which applies to the entire network, even if placed at a single node. There are some exceptions, however, in a few older transceivers. Should I place an external failsafe biasing network at all my receiver nodes? External failsafe biasing is ideally only placed at one node. If it is placed at each node, the pull-up and pull-down resistances need to be much higher. The drawback to this is that the pull-up and pull-down strength is now a function of the number of nodes installed. There are a few different ways grounding can be accomplished in an RS-485 system. In example A, the system is vulnerable to high ground potential differences. If the ground potential difference is greater than the limit of the device, it could stop working or even be damaged. In example B, if a high ground potential difference is present, a large group of loop currents could form, which can be coupled into the data lines as common mode noise. Example C is recommended by the RS-485 standard. Adding the series resistors lowers the loop current, but the noise could still exist. When grounding an RS-485 system, the ground potential difference should not violate the common mode specification for the transceiver, which the RS-485 standard specs to be at least -7 volts to +12 volts. Some transceivers support even higher voltages from -20 volts to +25 volts. In cases where very large ground potential differences could occur, an isolated RS-485 transceiver should be used.